So well, okay, we have one question that we have a small point mass m, and it is constrained to move in this cylinder. Okay, this is a point mass. Sorry, I think I should speak. ये देखिए, ये आपका पॉइंट मास है जिस पे चार्ज Q है, और ये कंस्ट्रेंट है इस सिलेंडर में मूव करने के लिए. ओके, और नीचे बेस पे एक चार्ज Q रखा हुआ है जो इस पे इलेक्ट्रोस्टैटिक फोर्स लगाएगा. जब हम इसमें स्लाइटली डिस्प्लेस करते हैं, देखिए ये डिस्टेंस यहाँ से y नॉट है. अब देखते हैं जब हम इसको y स्लाइटली डिस्प्लेस करते हैं तो ये SHM शो करेगा. तो हमें इक्वेशन निकालना होगा, डिराइव करना होगा SHM का. देयर आफ्टर हम लोग गवर्निंग इक्वेशंस देखेंगे SHM का, उससे हम जनरल इक्वेशन से कंपेरिजन करेंगे और उसके बाद हम एंगुलर वेलोसिटी निकाल लेंगे और एंगुलर वेलोसिटी से हम टाइम पीरियड निकाल लेंगे. तो हमें टाइम पीरियड निकालना है इस सिस्टम का. ओके, आप देख सकते हैं इसका मोशन हम डिफाइन करेंगे, मोशन कैसे होगा, और मोशन की इक्वेशन से हम लोग एंगुलर वेलोसिटी निकालेंगे. तो दिस इज योर क्वेश्चन. ओके, सो आप देख सकते हैं इक्विलिब्रियम कंडीशंस पे, इसलिए हम पहले ही लिख दिए क्योंकि हम रिकॉर्ड कर रहे थे तो थोड़ा रिकॉर्ड नहीं हो पाया था, तो ब्लैक बोर्ड पे लिखा हुआ था, हम उसे एक्सप्लेन कर रहे हैं अभी. ठीक है, तो mg बराबर आप देख सकते हैं ये इलेक्ट्रोस्टैटिक फोर्स होगा Q बाय 4 पाई एप्सिलॉन y नॉट स्क्वायर. y नॉट यहाँ इसका डिस्टेंस है. जब हम डिस्टर्ब करते हैं स्लाइटली, आप इसे स्लाइटली डिस्टर्ब कर दें, यानी y नॉट इसे आप मूव कर दें, अब देखिए कि नेट डिस्टर्बिंग जो फोर्स होगा ये होगा Q 4 पाई एप्सिलॉन नॉट y नॉट प्लस y का होल स्क्वायर माइनस mg बाय ma. अब ओके, और नेट डिस्टर्बिंग फोर्स इज ma. ओके, दिस इज न्यूटन सेकंड लॉ. आप कह सकते हैं कि y नॉट हम जिसे नीचे ऐड किए तो ये तो दोनों बराबर है, तो ये तो कम हो जाना चाहिए था. ओके, साइन कन्वेंशन में कोई लेना देना नहीं है क्योंकि रिस्टोरिंग फोर्सेस होगा जिसे हम नेगेटिव साइन ले सकते हैं. सिर्फ हमें लेना है ये साइन कन्वेंशन, हम बाद में ले सकते हैं. ओके, तो हम देख सकते हैं कि इसे आप सॉल्व कर ले, तो आप जब एक्सप्रेशंस को बाइनोमियली आप एक्सपैंड करेंगे तो ये इक्वेशन होगा. y नॉट कॉमन ले ले और y नॉट कॉमन ले ले, और फिर आप y नॉट स्क्वायर यदि बाहर निकालते हैं इस ब्रैकेट से तो आपका ये वैल्यू आएगा जो mg से सब्ट्रैक्ट करने पे मास गुना एक्सलेशन होगा. आप न्यूमरेटर से ऊपर ले जा सकते हैं, तो आप इस पे -2 पावर दे हो जाएगा, और फिर आप इसे बाइनोमियल एक्सपैंड करते हैं तो यह हमारा हो जाएगा. ये हमारे एक्सप्रेशन है. ओके, now we have a simple equation of motion here. Okay, हम लोग करते क्या है, just like disturb it and write the net unbalanced force. Now rest तो just follow the pattern. Okay, बस उसी पैटर्न पे आ जाएगा आपका इक्वेशन. आप इस इक्वेशन को सॉल्व करने के बाद आपका फाइनल रिजल्ट उसी फॉर्मेट पे आएगा, उसी इक्वेशंस पे आएगा. तो हमारा ये देखिए आप, देन नाउ सॉरी Q by 4 pi epsilon naught y whole square minus QQ by 4 pi epsilon naught y naught का whole square, this is epsilon naught y naught का whole square into 2y by y naught minus mg is equal to mass and acceleration. Okay, and this is going to be cancelled off because it is equilibrium. You see, both are equal. Now we have acceleration and this is mg, so you can write minus mg because you don't need to do, we haven't defined this term y naught. Okay, so just you can take it. Okay, this is y naught. this is going to be mg 2y y naught बराबर, so here mass m. So acceleration we have minus 2g y naught into y. So now we are done with the problem. We have reached the equations here, and this is general equation of SHM. Acceleration is nothing but d to y by dt square plus 2g y naught, so 0, and this is y, and this is omega square. Omega square is 2g y naught. Okay, you know acceleration is equal to minus omega square x. X is displacement. Here y displacement. Don't worry with x and y. Then omega we have under root 2g by y naught. Now what is the time period? Time period. Okay, this is your annual omega. Okay, annual frequency. Well, we have reached the answer. This is your answer. Okay, let us now consider a non-conducting ring, and one half it has a positive charge distribution, and here we have negative charge distribution. This is a non-conducting ring, non-conducting ring having mass m, and it is at rest initially, and we apply uniform field, electric field in this direction. So I think this is making arrangement of positive and negative charge separated by a small distance, so it can make a configuration like dipole. So we can find the dipole moment, and it is an electric field, so torque will act on it. Okay. And you see how negative and positive charge are distributed uniformly. So charges, you see negative and positive charges are distributed uniformly. Well, now what you do, disturb this configuration, give a small angular displacement about this vertical line theta. Okay. The ring is given a small rotation about the vertical diameter of ring, and then released. Okay. Ring is given a small angular displacement, then released. Then you need to find, it will oscillate. Okay, definitely it will oscillate. Then the time period of oscillation of this ring. This is, I want to find. Well, we can use some sort of mechanics equation of motion, and this is more or less classical SHM. So first, how can you develop the equation? The torque, you can understand this basic equation. Dipole moment, and this arrangement is, making a dipole. So dipole moment cross electric field, it will give the electrical torque. And what is this? P is sine theta, and theta is very small. Okay, so you can write P theta. So how can you find the dipole moment of this arrangement? Okay, take this section, d theta, and making an angle theta from like this. Also in this section again, symmetrically cut this. Symmetrically take this section, and symmetrically means again this angle is theta, and a small angle d theta. So you have to define point function for the charge distribution. Say lambda, and say lambda is charge per unit length. Okay, it's a point function. I have defined it so that we can take this elementary charge present on this ring. This is a small section. So what is dipole moment? It is nothing but charge. So this is the distance. So two charges, positive and negative charges, having separation this much. Okay, well, this much. This and this. This and this plus this. This is the separation. And what is dipole moment? dp, say, is dq into, this is r cos theta, this and r cos theta we have, 2r, cos theta, and we can take dq. Dq is lambda, and this distance, this length, r d theta, lambda into r d theta, 2r cos theta. This is your dipole moment of this configuration of entire system. Okay, then perform the integration, we can find P is the dipole moment. Well, okay, radius is fixed, lambda 2, and you can write here q by pi r. This positive charges, this has length pi r, and whole perimeter is 2 pi r. So half perimeter has length pi r. So we will put later 2 lambda r square cos theta d theta, and you perform the integration is to minus pi by 2 to pi by 2. This, if you consider this angle to about anti-clockwise, and we can also consider this section, below this, in this quadrant, then you have to transverse this angle in this direction, and both are in a positive direction, and it will go to this one, it will transverse angle of pi by 2, and this will also transverse of angle pi by 2 but in opposite direction. So we have taken minus pi by 2 to pi by 2. Here minus pi by 2, and upside we have taken this pi by 2. And you know this is going to be 2. Okay. This is I think this is dipole moment. So this is going to be 2 integration. When you evaluate this integration, you can find this value 2. So we have 4 lambda r square. So we have found the dipole moment of the system. You can also ask a single question. Find this for this given compression and charge distribution is given like this. Then you need to find the dipole moment. Then this is the dipole moment. But one step ahead, we have equation of this torque. Then why don't we not apply this equation? Find the time period of this oscillation of the ring. Well, so we can write 4 lambda is equal to q by pi r and r square. So we have 4 q r by pi. Okay, this is the dipole moment of this configuration of the system. Now we have torque is Pe sine theta, and dipole moment is 4 q r by pi e sine theta. So we can write torque is equal to 4 q r by pi e theta because sine theta is going to be very small. And this is restoring in nature. Now, as usual, light inertial torque. Okay, we have I into alpha i's ring mr square moment of inertia, and here coordinate. Okay, we have spacing all this thing in theta. Then why don't write alpha as this one, and this is you can restore it. From this balance, this will be equal but in a opposite direction, and now you can develop the equation. So we have d2t by d2 square plus 4q are going to cancel out. So we have 4q pi mr e and theta is equal to 0. This is your omega square. So omega, and you can say 4q pi mr. You can write another time period. Okay, you can find the time period. Okay, well, now we have time period 2 pi by omega 2 pi. This is your angular frequency. Omega is pi mr by 4q. Oh, sorry, E. I have missed this E. So you can also write here E. Now sometimes you need to be very careful. Okay, I can miss something, but be careful. You can find my mistake. Okay, well, so this is your answer. Okay, now I tell you that is today. Now, what is the time? I tell you, time is 1 p.m. at night, and at this time I make fun and I enjoy while making the video. So Just I am doing for myself, and maybe somebody can entertain it, somebody may benefit it. Okay, but I'm enjoying. Okay, the way I enjoy it at night is in this way. I just practice for myself. Well, we have now a configuration. Here it is semicircular and the charge distribution is like that, positive and negative, uniform distributed. The question is thin glass rod is bent into a semicircle of radius r, a charge plus q is uniformly distributed along the upper half So this is charge plus q and this is charge minus q, like this. You have, this is the point P and you need to find the electric field at this point P. Now you have to find electric field at this point. This is your question. You have to find electric field at this point, and this is origin. So this is the middle point. Okay, well, and this is on the axis. Somewhere on the axis. This distance is r, of course. So this is r. Then you have to find the resultant electric field due to this configuration. You see how the charge is distributed. Lower half minus q, well, upper half plus q, and uniformly distributed. Okay, this is question. So this is the point P. You can take again theta, and the section this is r d theta. You have to find the lambda. Just define lambda. Lambda is nothing but q by whole length is pi r, then pi r. This is pi r by 2. So this is your lambda. You did now defined how the charge distributed over this length, and it's a point function. So now we have this dq. Again now, when lower half, you can again consider symmetrically r d theta. Well, so it is a positive charge. So this is, okay, don't be confused with so much line. I'm just making this, okay, r d theta. And this is electric field due to the negative charge, this is the positive charges, and both are equal. So in between these two lines of force, we have an E net. And this is theta. So this will be 90 minus theta, so this is going to be theta. For 90 minus theta, both angle will be equal, so 90 minus theta. So here we have E cos 90 minus theta, then we have E sin theta. And due to this component, another E sin theta. Just add due to this component and due to this, both in this direction contributing E sin theta and E sin theta. So we have E sin theta and E sin theta, we have 2E sin theta. Electric field. Now let's write E is nothing but dq by 4 pi epsilon naught r square sin theta. Now what is the dq? 2 into lambda, cancel it by 2, lambda r d theta 2 pi epsilon naught r square sin theta. Now this is the iiest. Now I can put lambda 2q by pi r into r d theta sin theta by 2 pi epsilon naught r square. Going to cancel dot, so we have 2 is going to cancel dot q by pi epsilon naught r square sin theta pi square sin theta into d theta. Okay, I think I'm not missing anything. So 0 to pi by 2. So your answer is q by pi square epsilon naught r square. This is your answer, the electric field at this point. So this is your electric field. This is your answer. So now do another problem. Now you see a system of this ring, and center we have thin wire, and its radius is r. R is radius of ring. And this is long wire. Charge is uniformly distributed, and total charge is q. This is a total charge q distributed uniformly on the ring, and here lambda. This is this defines how the charge distributed over this wire, and this wire is very long. This wire is very long. Now you find interaction of force. Interaction of force between the ring and wire. Well, this is a question. Okay. It can produce the electric field in this direction. And also in this direction. and value of this electric field E over this ring is, because it's constant about this length r, lambda by 4 pi epsilon naught r here, and you see this is charge is dq, so df is nothing but dq E into dq, this is a force. Integrate this, you will find the force, and integration performs lambda 4 pi epsilon naught r into q. Okay, you can also find, take this element and force here, integrate it with 0 to infinity, you will find the same answer. Okay. So this is your answer, interaction of force of this system. Now another question. Find the force experienced by a semi-circular rod having a charge Q as shown in figure. Radius of wire is r, line of charge with linear charge density lambda passes through its center and is perpendicular to the plane of wire. Okay, so this is line of charge, very long, and we have like this a rod of semicircular in this plane, perpendicular. This is perpendicular to the plane containing this ring, semicircular ring, or rod you can say. Now, what is the force experienced? This here lambda, and it has given a charge Q distributed over this, this length. Now we have to find the force of interaction. Okay. Well, this is your system, minus infinity to plus infinity, and here lambda charge, you define with lambda, and here this is radius r, and it have charge q. Now define this, how this is distributed. First you need to always to define how the charge is distributed, then lambda to say is equal to q by pi r. You consider this section, and this here electric field is in this direction, and nothing but lambda 2 pi epsilon naught r. You know this infinite wire. So under section again, okay. So you find this component E cos theta. So force is what? E cos theta into dq. Electric field just express 2 pi epsilon r dq is equal to lambda 2 r d theta. This is dq. So we have q by pi r. This is lambda r d theta cos theta. Lambda q by 2 pi epsilon naught r pi square cos theta d theta minus pi by 2 to pi by 2, and this is going to be lambda q. This is again, its integral value is 2. We have pi square epsilon naught r. I think I haven't missed anything. So this is your force of interaction, and this is your answer too. Well, we can do some other problems. Now we have large sheet. Question is, we have a question. A large sheet carries a uniform surface charge density rho and a rod of length 2L has linear charge density lambda on 1/2 and minus lambda on 2/2, like this. This is z axis and this is y. This minus infinity to infinity, minus infinity to infinity, and we have a rod making an angle theta. This is axis x, and here charge distribution is of positive lambda and here is minus lambda, and hinged at point this, hinged at point O, midpoint. This is the midpoint. It has a length 2L, total length is 2L, so this length will be L and this length will be L. Then we have to find the torque experienced by the rod. Find the torque experienced by the rod. This is the question. Okay. Okay, you have to find the torque. And electric field, you just, okay, I just make it a clear picture that like this, hint at this, and O here plus lambda, like this length is L and this length is L. Here positive charge plus positive charge distributed, and along this length minus negative charge is distributed. So why don't you consider a small distance x and text dx, and dx has dq charge lambda into dx. And again, electric field here sigma by 2 epsilon naught. This is the electric field due to seat. So force will act along this direction. Another way you can consider that at similar distance x we have another df is same, df and df, this is same, and two parallel forces, and torque is nothing but df into r perpendicular, and this was theta. And we have x sine theta, and this angle with theta, again this x sine theta, and another one, this is x sine theta. So total length is 2x sine theta, so we have df into 2x sine theta. Well, and df is nothing but electric field into dq into 2x sine theta. Now sigma by 2 epsilon naught. Now what about dq? dq need to be defined as lambda naught dx d2x sine theta. Actually d tau is, so when d tau is integrated it will give the total torque. And the total torque is sigma constant, you can keep it outside. 2 is going to be cancelled out. Lambda sine theta is also constant, x dx. Now we have sigma lambda sine theta. So now this is 0 to L. We have L square by 2. Now this is the torque, sigma lambda L square sine theta 2 epsilon naught. So this is a torque experienced by this rod having length 2L. Okay. Angle is, this is the angle between x and along this length and x axis makes an angle theta. So this is source angle sine theta. Well, now suppose this is a conducting a spherical sail. This is conducting a spherical sail, and outside is earth. This is earthing, sign of earthing, and is given a Q1 charge and here Q2 charge. Then find the Coulomb force on Q2. This is your question. You have to find the Coulomb force on Q2. Suppose Q1, then it will induce the charge minus Q1, and here I don't know, say X, And on earthing, potential, we haven't studied potential yet, but okay, anyone can understand this. Potentials would be 0. Let's make it potential here. Let's write equation of potential. That is q1 by 4 pi epsilon naught, like this radius is r, and this minus q1 by 4 pi epsilon naught r. Potential at surface is equal within the conductor and a charge q, and will produce here potential q by 4 pi epsilon naught r, and also on the surface x by 4 pi epsilon naught r, and this is going to be 0 because you're writing potential on the surface, and this is going to cancel out. This means x is equal to 0. Here on the outer surface has no charge. Outer surface has no charge, then no force will act on it, because outer surface will always respond outside, and here we have no charge, and this means nobody is going to apply force on this. So force is 0. This is your answer. Well, then what happened when this is not Earth. Again, do these problems. If this is not Earth, not Earth, then what will happen? You have Q charge is enclosed by this. You can see this surface conductor, a spherical shell. I just enclosed this charge Q, and we have put a charge Q to outside. Then we are interested to find the Coulomb force on this charge. Okay, so this will induce to minus Q charge, and since charge is conserved, so we have Q charge here. Okay, so now Q, this is response to this one, and we have QQ by 4. This is the distance from the center, say R. So we have 4 pi epsilon naught R square. This is the force. This means if you put a charge inside a spherical shell, then the Coulomb interaction will be same. No effect whether you encase this charge under this spherical shell or not. It will respond the same way if suppose it is not encasing with this spherical shell. So force is same. Force is going to be same. And this is some basic question. I think everybody should know this. Okay, well, now another problem. 3 charges Q, Q and minus 2Q are fixed on the vertices of an equilateral triangular plate of HA. Now this plate is in equilibrium between 2 large plates. this is two large plate, and this has surface charge density sigma 1 and this has surface charge density sigma 2. Fine, and you just put this triangular plate here. Now we have centroid. So axis is passing through centroid, and moment of inertia of the system about the axis passing through centroid is I. Then find the time period of oscillation. Find the time period of oscillation. Well, this is a question. Okay, आप यहाँ देख सकते हैं, this is how किस तरह चार्ज रखा हुआ है. यहाँ पे आप -q चार्ज है, यहाँ पे q चार्ज है, यहाँ पे q चार्ज है, और इक्विलेटरल ट्रायंगल, तो ये एंगल कितना है 60 डिग्री. आप देख सकते हैं ये डायपोल मोमेंट here p is equal to q into a, again here p q into a, and this is a vector quantity. So resultant dipole moment we have. So under root p square plus 2p1 into p2, angle is cos 60 degree. So we have p square plus 3p square root, we have root 3p. So resultant dipole moment is 3qa. Okay, now it's placed in electric field. What is the resultant electric field here? This is sigma 2, this is sigma 1, and it will produce electric field in this direction, and this will produce an electric field in this direction, and both are opposite. So we have E net here, sigma 1 minus sigma 2 by 2 epsilon naught. Well, now what is the torque? P cross E. Now we have torque P cross E enter with root 3 QA E sin theta. This is your torque. We are storing torque, you can say, you can take it minus, okay, negative charge. Theta is very small, so you can consider it theta, and inertial torque is moment of inertia into d2 theta by dt square. Using these two equations, we can develop a general governing equation of SHM. So I d2 theta by dt2 square plus root 3 qa e theta is equal to 0. So d2 theta by dt square plus root 3 q a e theta by I is equal to 0, and this is omega square 3 q a, and you can write I is equal to 0. Sorry, it's not 0. This is omega square. Now your omega is nothing but root under 3 qa sigma 1 minus sigma 2 not I. Okay. Now time period is nothing but 2 pi by omega. This is your answer. Okay. Now, other problems like this. This is inclined plane having θ1, and we have a charge q. Is put like minus q and plus q here. This is a wheel. Okay. So question is, a wheel having mass m has charges q and minus q on diametrically opposite points it remains in equilibrium. It remains in equilibrium on rough inclined plane in presence of uniform vertical electric field E. You have to find what is the electric field E, and E is along this direction, vertical, and it is in equilibrium. Okay. So you find this is mass m, so of course mg sin theta will act downward, and okay, so it is in equilibrium, so we can apply the torque equation, apply, you can find, you can balance the torque equation about this point, contact point. Oh, this is the contact point. So weight, this is the weight, mg sin theta. So torque due to mg sin theta is equal to mg sin theta into r. Now here, this will act downward QE, and this will act QE parallel to this line, perpendicular to this line. And this is, of course, this angle is theta, and this is your theta, and this is perpendicular distance, because torque we have force and into perpendicular distance. Okay, apply this, and this is your perpendicular distance. So torque due to QE, this electric force of this, I am talking about this force towards, we have QE into 2R sin theta, and due to this charge, since this is passing through this point, so torque due to this point will be 0. So since it is in equilibrium, so two torque will balance each other. So we have mg sin theta into r is equal to QE 2r sin theta. Sin theta is going to cancel, r is going to cancel. E is mg by q. Well, this is our answer. Am I not missing anything? 2, sorry. This is your electric field. Okay, then next problem I'll do some next classes. I will do some good problem. Thank you.